Hi everybody, it's Professor Lashane back again. I'm going to shoot a video or videos, it might be two, for section 6.1, confidence intervals. So let's go through that section. I'm on page 298 in the book, and I'm just going to walk through the examples in the book. And again, you should have the formulas page that from chapters 5 and 6 formulas that I have in the week 11 and 12 modules. You should print that out and have that page available. Those formulas will all be available when you take the tests and so on. So I'm going to example 1 on page 298. And we're going to keep using this example. Actually, we're going to keep going back to it for some of the other examples here. So it says, a researcher is collecting data about a college athletic conference and its student athletes. A random sample of 40 student athletes, so that's our sample size, 40, which is considered a large sample, is selected, and their numbers of hours spent on required athletic activities for 1 week are recorded in the table at the left. Find a point estimate for the population mean mu, the mean number of hours spent on required athletic activities by all student athletes in the conference. So the best point estimate for the population mean mu is the sample mean x bar. And we know to calculate a sample mean back from chapter 2, we add up all the data values. So if we were to add up those 40 data values in that table in the left-hand margin on page 298, it says it's going to add up to 842 if you were to check that. And then we're dividing by 40. And so when I put that in our calculator, 842 divided by 40 is going to give us 21.05. Now, how do you round? Remember, the general rounding rule means you carry one more decimal place in the original data. If you look at the original data, the number of hours are whole numbers with 0 decimal places, so we're going to carry 1 decimal place. Round to the 10th, so we look at the hundreds places of 5, we round up. So it's approximately, our point estimate is approximately 21.1 for our population mean. But that's not a great point, that's not a great estimate, it's just a single value estimate. So a better way to do this is to do what's called an interval estimate. And so that's what we're going to use for our example 2, which is on page 300. We're going to learn to make something called an interval estimate. So in order to do an interval estimate, you have to first calculate a margin of error. So we've got a formula for margin of error, z sub c, critical value of c, times sigma, the population standard deviation, over the square root of n, the sample size. So how do you get z sub c? Well, we generally use 90, 95%, 99% levels of confidence. And if you look at the negative z side of the table at the bottom, you've got your critical values. For instance, if you have a 90% level of confidence, that would mean that the area under the standard normal curve between the critical values of z, positive and negative, that area there would be 90%. And that then means there's 5% in each tail of the area. And if we look up the left tail, what happens is we get a critical value of z, which is halfway between 1.64 and 1.65. So we actually average them together, 1.645 for 90% confidence. But again, you don't have to go all through this because we've already done all the work. We're generally going to just use 90, 95, and 99%. There's also 80% at the bottom of the Z table, which again you can find in the week 11 or 12 module. Print those out so you have those tables in front of you. So to continue with example 2, it says use the data from example 1, where remember from example 1 the sample size was 40 and a 95% confidence level. So for the 95% confidence level, again, you look at this at the bottom of the Z table on the negative side, and you find the critical value for 95% to be 1.96 here. And remember also back, and it also said that you need the, assume the population standard deviation is 2.3 hours. So that you need. So we're going to calculate the margin of error. So we're going to take z sub c, 1.96, times sigma, 2.3, over the square root of n, 40. And so again, it's really critical that you know how to do the square root of in your calculator. Multiply straight across 1.96 times 2.3 divided by square root of 40, and that's going to give you 0.7127 something. And the original data were whole numbers, so we're going to carry one decimal place. Looking to the right in the hundreds place is a 1. So our margin of error for this problem in example 2, which we're going to use again in a minute, is 0.7. Let me move that up. So it's 0.7. And so what that means is that we can assume that for the margin of error, it's the maximum distance between our point estimate and the value of the parameter it's estimating. So the margin of error with a 90% level of confidence, 95%, so we have a 5% chance of being incorrect here. The margin of error is going to be 0.7 hours. That's the maximum error we're willing to tolerate. Those of you who are science students know about standard error when you're doing science experiments. So now we're going to go up and we're going to construct a confidence interval, and we're going to go to example 3, which is on the next page, page 301, using the same information. So this says, use the data from example 1 to construct a 95% confidence interval for the mean number of hours spent on required athletic activities by all student athletes in the conference. So for a confidence interval, again, this is on the formulas page that you have. Our formula is x bar, sample mean, minus e, margin of error, less than mu, less than x bar, sample mean, plus e, margin of error. And so this less than mu, less than part stays static. We're just going to put in numbers here and get those two endpoints. And so in order to do this example 3, we go back to example 1, and we know from example 1, remember, that x bar was 21.1. And from example 2, for a 95% confidence level, the margin of error was 0.7. So putting that information in, we have 21.1 minus 0.7 less than mu less than 21.1 x bar, sample mean, plus e, the margin of error, 0.7. So we're going to subtract on this end, and we're going to get 20.4 is less than mu is less than, when we add here, 21.8. So what we're saying is with a 95% confidence level, and we have a 5% chance of being wrong here, we think that the true mean number of hours spent by student athletes per week on required athletic activities falls between 20.4 and 21.8 hours. Now, the way the book and my stat lab sometimes show it is they show it in interval notation. Those of you who took algebra in high school or took Math 92 with us, the way to show this interval notation for this compound inequality is to have the left endpoint 20.4. It's not included because it's not or equal to, so parentheses, comma, the right endpoint 21.8 with a parentheses. So that's example 3. So now if we go to example 4, it says take the same information from example 1 and now construct a 99% confidence interval for the mean number of hours spent by student athletes in that conference. So example 4, page 302. So now we want 99% confidence. So remember the sample size was 40. And remember they told us back in example 2, we kind of have to keep going back and looking for things here. They told us that the standard deviation was 2.3, but now we want 99% confidence. So to have more confidence, we're going to need a wider interval to have more certainty about our estimate. And so for 99% confidence, going to the Z table or on your formulas page, you see that the critical value for Z we're going to use is 2.575. By the way, we only use the positive value because we're dealing with measurements, and if we use the negative on the negative side of Z, it would mess everything up in our measurements. So we just use the positive value for 2.575 for the critical value. So now we're going to calculate a new margin of error using Z sub C, 2.575, times sigma 2.3 over the square root of the sample size, 40. And so we're going to put that in our calculator. You can multiply straight across 2.575 times 2.3 divided by the square root of 40 equals, we've got 0.936. Again, the original data were whole numbers, the number of hours that athletes were spending. So we're going to carry one decimal place in our answer. Since it's a 3 in the hundreds place, we're going to call that 0.9 for our margin of error. So now we're going to go to do our confidence interval. That's the formula on the formulas page for the confidence interval. X bar, which was the sample mean way back from example 1, we calculated, remember the sample mean was 21.1, so we're going to keep using that information. So X bar 21.1 minus my margin of error for 99%, 0.9, less than mu, less than X bar 21.1, plus our margin of error 0.9. So subtracting, we're going to get 20.2 is less than mu is less than 22.0. So with a 99% level of confidence, we think that the mean number of hours spent by all student athletes in that conference per week on athletic activities falls between 20.2 and 22.0 hours, but we do have a 99% level of confidence, so we have a 1% chance of being wrong in this estimate. And so again, the way my stat lab will probably have you put this answer is it'll give you parentheses, left endpoint 20.2, comma 22.0 for the right endpoint with a parentheses. So that's how you'll show it in my stat lab. So we'll go to example 5 and do one more confidence interval, which is on page 303. So on example 5, page 303, it says a college admissions director wishes to estimate the mean age of all students currently enrolled in a random sample of 20 students. It's kind of a small sample here, only 20 students. The mean age is found to be 22.9 years. That comes from the sample, so that's X bar, the sample mean. From past studies, the standard deviation is known to be 1.5 years. So we'll assume that's from the population. They didn't tell us it was from a sample. And the population is normally distributed. That's important because we don't have a large sample of 30 or greater, but because we have a normal distributed population, we can keep going with all of our formulas with normal distribution. Construct a 90% confidence interval. So we want a 90% confidence interval. So the critical value for Z you can either get from the formulas page or the bottom of the Z table on the negative side is 1.645. So we're going to use that for our critical value for Z. For a confidence interval, first you calculate the margin of error, Z sub C 1.645 times sigma 1.5 over the square root of the sample size 20. So putting that in the calculator, we have 1.645 times 1.5 divided by the square root of 20 is going to give you 0.5517 something. And the original data, they didn't show us the original data, but usually if you ask someone how old they are, they're going to say, I'm 19 or I'm 27. They're not going to say I'm 19.7. So probably that was whole numbers plus the sample mean had one decimal place. So we'll match the sample mean with one decimal place, and the tens place is a 5. We look to the right as a 5. So we're going to call our margin of error 0.6. So now going to constructing our confidence interval, X bar minus E less than mu less than X bar plus E. Putting in that information, X bar, sample mean they told us was 22.9. Minus E we just calculated was 0.6. Less than mu less than X bar 22.9 plus the margin of error 0.6. So subtracting 22.9 minus 0.6 is going to give me 22.3. Less than mu, less than 22.9 plus 0.6 is 23.5. So we are 90% confident. We have a 10% chance of being wrong that the true mean age of students at that college that are currently enrolled is between 22.3 and 23.5 years, but 10% chance of being wrong. So again, putting that, and that's our estimate for the population mean mu. So putting that in interval notation, parentheses 22.3 comma 23.5 parentheses, and I will shoot another video to go to example 6. See you in a minute.